The project of our group is full reference image quality assessment for different resolution. Nowadays, the device people are using to acquire visual information vary from television to smartphone with different resolution but same content. Until now, most image quality assessment algorithms are designed to assess images with exactly same pixels. As a result, an algorithm to analyze images with different resolution but same content is in need. A typical full reference image assessment algorithm to assess image with exactly same pixel is structure similarity index measurement, which consists of luminance comparison, contrast confirmation, and structure comparison. There are many three steps to evaluate the performance of an algorithm. The first step is to fix the objective parameters and subjective scores. The second is to use obtained match equation to calculate the objective score, and the final step is to compare the objective score and the subjective score. There are three features used to evaluate the performance of an algorithm. They are accuracy, monotonicity, and consistency. Accuracy is measured by linear correlation coefficients, which is the closer to 1 the better. Monotonicity is measured by Spearman rank order correlation coefficient, which is also the closer to 1 the better. The consistency is measured by mean square error and the mean absolute error, which is the smaller the better. And the figure in here shows these two features. Our algorithm extracts three parameters from the high-resolution reference image and the low-resolution target image. The first is the SSIM calculation of low-frequency part of the reference image and target image. This is to measure the loss of quality in the process of degradation, multiplied by the human visual system parameter acquired by distance from observer to screen, the height of screen, and the resolution of image. The SSIM is also able to reflect the influence of observing patterns. The second is a high-frequency proportion to the autocurrent coefficients, representing the loss in detail due to the reduction of resolution as well as the content difference. This has a high correlation with the content and the resolution. For image with same resolution, the image with rich in details has a higher proportion than image with less detail. For image with same content, the higher the resolution is, the less the proportion is. As a result, the proportion satisfies the requirement of extracting parameters related to content and the resolution. The third parameter we used is the half high-frequency part of reference image is the rest part of reference image to an imaginary target image with half height and width of the reference image. The calculation process is similar to the proportion of high-frequency part and only related to the content of image. The purpose of introducing this parameter is to let the high-frequency part more emphasized on the difference in resolution. And the figure on the right shows the method of calculation. The blue part is the low-frequency part, and the white part is the high-frequency part. And the part shadowed by red lines is the half-high-frequency part. The image dataset is created by ourselves. We choose 8 images with different amount of detail in the information and resolution of 720 multiplied by 1280. Each scene has 3 resolutions, dumped into these 3 resolutions, and degrade them with noise, blur, and JPEG compression. and in experiment, the distance from observer to the screen is fixed as 60 centimeters. And we also use OpenGL to guarantee the image display on the screen with same resolution of it stored. And for the training dataset, we use for each resolution we have chosen 3 images randomly with score ranging from 1 point to 5 points for each screen. And for the total 8 scenes with 3 resolutions, the number of training images is 72 out of the total 504 images. Here are the 2 test examples. The upper one is less in details, and the one below is rich in details. And also, this is the image about the test procedure, and we can see that the eyes and screen distance is fixed by 60 centimeters. Now we are going to show you how we test it. First, we choose the reference to be 720 and multiply by 1280, and record the subjective scores in this file. Now the observer can type their rate on this screen and watch the image with exactly the pixel it stored. When finished typing, the image will automatically change to another one. It is the same when we change the resolution to be the 540 multiplied by 960. When typing, it can automatically change. From the result trained by the decision tree model, our algorithm is superior to SSIM algorithm in overall performance and each image resolution. Also, we studied the influence introduced by the different training methods, and the high LCC and SROCC and the low MSE and MAE of regression model trained by gradient boosted tree model and the support vector regression with RBF kernel illustrate that these 2 training methods as well as the decision tree model are suitable for training an image quality assessment model. But since it's different when looking at lasso regression and ridge regression, both belong to linear regression. Although they are high in LCC and SROCC, but they are high in MSE and MAE, illustrate that the linear regression model is not a good choice for training an image quality assessment model. So we can draw the conclusion that the training method is going to significantly influence the performance of model, and the linear regression model is not so suitable for training image quality assessment model. And our algorithm is good enough to assess the quality of image with different resolutions. One possible further work is to extend our algorithm from gray image to color image. Thank you.